Stars. Gotta love them. Gotta love them. I love them. You guys ready? Okay, phones away. Unless you're checking, like I said, on your sick children. We already know a little bit about stars. Stars are different colors. We're going to see some pictures of stars. Stars are different colors. What are the different colors you see stars?
Blue.
Blue. What?
Yellow.
Yellow. Red. Orange. Yeah, they're all different colors. Do you see them different brightnesses? No, we already talked about brightnesses. That sheet I gave you for November, down here in this lower hand corner, you guys told me that the bigger the dot, the brighter the star, and that is totally it, okay? The bigger the dot on here, the brighter the star. We call it its magnitude. If you have a magnitude -2 and you have a magnitude +2, which is brighter, the -2 or the +2? The -2, exactly, magnitude. And there at the end of when we talked about the brightness of stars, I introduced something that feels strange. I said, if a -2, you're like, dang, that's so bright. But is it really bright because it's close, or is it bright because it's just like got all this energy that it's creating in its core? And the answer is it could be either. So we last left, and actually this is an important thing. This lowercase m is what we call apparent, and I can never spell apparent, so I apologize in advance. Apparent, like it appears, apparent magnitude. And that is the way it appears. And this is in the sky. In the sky. You're like, well, what's the other one? Okay. The other one is a capital M. I'll try to kind of round off my things. A capital M, and this is absolute magnitude. Oh, goodness. And for this one is placed, I'm going to say placed on line from us, and it's going to be 10 parsecs away. Shh, it's hard to talk over you. I'm finding myself getting louder and louder. So it's placed 10 parsecs away, which in terms of light years, that's 3.26 LY. LY stands for light years. So the awesome part of this is you have removed the effective distance.
How do you say parsec?
Parsec. P-A-R-C-E-C parsecs. P-A-R-C-E parsecs. I'm pretty sure it's that. It's got like 2 C's. It's kind of a weird word, parsecs.
And then 3.26
LY, light years.
Light years. Okay.
Yep. LY, light years. Yep. So it's like the absolute magnitude makes a lot more sense when you're trying to understand like the science of a star. And I think I mentioned this before, that this one is what we care, this is what science cares about. Science cares about this. When we come to characterizing stars, we care about that. And as it turns out, I don't know if you guys maybe remember this, the energy in stars are created in starts letter C. What's the center part of the Earth's or the sun? Core, yep. So this is the core of a star, yep. And this is kind of the other part of the star. This is the energy coming from the star, and we call the energy coming from the star its luminosity. And a very common unit that we use with light bulbs, the units of measuring luminosity is watts. So the way it works is absolute magnitude, which kind of removes the effective distance, and luminosity, these say the same thing. They say the same thing about a star. They basically say, all right, you're at a certain standard spot from us, and we see you so bright in the sky. Or we visit you, and we see how many watts you're putting out. It's the same thing. Cool. Hot. Cool. So this is one of my favorite things. So like I'm a woman, no offense people, but so women in anything, including science, it just makes me smile. And so early on, these were women that actually helped look at stars. They looked at information from the stars. There was one guy that helped lead the team, but who cares? It was the women that I care about. So they actually looked at information from the star we call spectra. Do you remember the other day, and I had 2 lights in here, and you guys had little squares, and it was really noisy? Zzz. Okay, so picture those little squares. I didn't bring it in today, but picture those little squares. You guys saw those lines? Yeah. So these folks looked at those, like those little squares, that information coming from all these different stars. And one of the things that some people are good at are organizing. And so they organized. They organized a pile here, because these all look like the same lines. A pile here, same lines. A pile here, same lines. Okay, and they came up with 7 piles. So that's pretty cool. I'm going to go ahead and write this on the board, and I'll find my pen here. If you, in your notes, want to circle this, you can, because you're going to see it. It's kind of a common theme. And, oops, sorry. There's a little thing that goes along with that. Oh, be a fine guy, kiss me. I wonder if I deleted, didn't make that. Oh, be a fine guy. And some people use like mnemonic devices. It's a type of mnemonic device. Oh, be a fine guy or girl, kiss me. That sounds silly. But then you have all those spectral types. Oh, be a fine guy or girl, okay, kiss and me. This is the hottest, and I told you a minute ago that those ladies, this is the coolest, those ladies looked at little information coming from stars, and they had 7 piles. Those are 7 letters. 7 piles, 7 types of stars. Edward Pickering and his little computers. Okay. So I was going to see if this kind of gets bigger. Okay, it does. Is it getting bigger there? Okay, good. Now, I don't know, the things that you guys looked there, they might have looked a little different because those were not absorption lines. Those were emission lines. Those were bright lines. These are dark lines. But these are lines kind of like we looked at before. Can you see the, oh, be a fine guy or girl, kiss me? Okay? So, hot to cool.
What you say it's called again?
What's that?
What do you keep saying? Kiss me or what?
Okay, I'll put it on the board. It's a way to remember the 7 spectral types.
Okay.
So it goes like this. And it's not just me who thought of this. O, B, fine, guy or girl / guy, and K is kiss, and M is me. It's just a way to remember it. So, we can see some stars over here, some examples of stars. So what type of star in all of these is our sun? You see our sun here?
Yes. G.
It is G. Yep. So our sun is a G type, and I don't seem to be able to circle, but our sun is a G type. Do you guys see, well, I'll just kind of, let's see, I don't see, oh, I know. Some of us looked at that party star. Party star the other day is Arcturus. Okay? Betelgeuse, right? In Orion. So you can kind of see the hottest and the coolest stars. This next, so that's kind of how that works. Now it's all about, I can't remember in this class, did we talk about what makes the spectral lines, or that was my other class? It's the electron transitioning. I can't remember if we talked about that. It's the electron either skipping up to a higher energy level or falling down to a higher energy level. And this kind of talks about, I wouldn't worry too much about this. This just talks about how cool temperatures, getting warmer temperatures, that kind of talks you through why do we get these different spectral lines. Okay. So, a very busy slide, but amidst this very busy slide, you see the O, B, A, F, G, K, M. Okay? Which one's the hottest? O. O is the hottest. Yep. K is the coolest. Exactly. And again, this is just kind of showing you a little bit. These little arcs represent kind of why we get these different, why those ladies, when they were coming up with these 7 piles, why it happens that way. I have a lot of slides that kind of say the same thing. Now, this, I'm going to have to close that door. It seems so loud. It's just me. Okay? So I said that there are 7 spectral types, but as it turns out, each spectral type can be subdivided into 10. We're not going to worry too much about it, but for instance, you see up there we have the B0 and B6.
Yeah.
Okay. Which one's hotter, do you think, the B0 or the B6?
0.
B0 is hotter. Why?
I don't know.
Because it's closer to the, and this is the very hottest. Yep. So very good. Those are the A's, F, G's, K's, and M's. Yeah, so very pretty. So it's a fingerprint, you know, for you biologists in here, you know, how we can kind of use DNA to match a sample with person. So we can kind of use these lines to match a star with what we call a spectral type. So these are spectral types. All right. So here's one for you. The way you look at this slide is, I'm not sure I really buy into it, but I suppose I'm okay. We're going to have to kind of pretend that we're here. We are in the sun, but relative to another star, we are associated with the sun instead of that other star. So I suppose I'll buy that. What this is trying to tell you is that you guys see this green line here? Let's just say a star, and stars are not, oh, thank you. Stars aren't, well, actually I have a slide coming up to show you the Big Dipper. Who's seen the Big Dipper recently, right? The Big Dipper, we all know and love, actually, it's the stars that make up that set are kind of moving relative to each other. So over 10,000 years, it's not going to make that pattern. So stars move, okay? Our sun's moving. It has to move, or else we fall in the black hole in the middle of our Milky Way galaxy. So what this is showing you is we have a star that's moving. The star seems to be moving kind of catty corner like that. We can break down the star's movement into actually 2 kind of vectors. One is that star, in a way, is moving this way. Okay, we call this radial movement. And then it's moving this way. I know that says transverse velocity, but I'm going to put the word proper there. Okay, if you want to put the word proper, you can. The proper is side by side. When I say side by side, I mean side by side relative to kind of our motion of sight. So this is us, and this is that proper motion. Okay, this is us, and this is that radial motion. It's kind of like a spoke. So radial is moving directly out or towards. So it's more like a direct, out/towards. And we see, actually I have some slides kind of coming up, or some pictures to show you that if you want to see this proper motion, all you got to do is have a star that's not moving, and it moves relative to that star. Happens all the time. This radial motion, you're like, dude, I have no idea. And I'll kind of show you. We're going to actually use the Doppler effect to know that one. So 2 kind of motions that stars can have. So I mentioned the Doppler effect or Doppler shift. That was the whole, remember, I'm standing here, and I have a car that's making a sound. What happens to the pitch of the car as it comes towards me?
It's like higher.
The pitch gets higher. Yeah, it gets louder, and the pitch will go up. That's because like the sound waves are being squished. So this moving towards me is what we call blue shift, where they get squished. This moving waves we call red shift. Okay, now we're going to switch gears, and we're going to kind of think about what would that look like with a star. Well, we can look at that shift if we look at the lines. Okay, here we go. So the middle one is normal. The middle one, it's not moving at all. How would you explain the difference here? If I call this A, B, and C, the horizontal lines, what's the difference between A and B?
Toward the red side.
It moved a little bit towards the red side. It's hard to tell, but yep, it moved just a little bit that way. And we're going to see that the faster it's going, the more it's going to shift. Now, since it moved to the red shift, is it going towards us or away from us? What do you think? Away, exactly. Perfect. So you guys got it. That's an important part of understanding. I'm trying to write the word away. Goodness, this pen is not working. It's moving away from us because we have that red shift. And it's an important way of understanding stars, this radial motion. Not the proper motion, because we can see it kind of relative to other stars. Radial motion. So what do you think this one's going to do?
Move toward us.
Move towards us. Did the lines move over? Now this, remember, we're going to compare B and C. Because B are stationary, so C moved towards the blue end, didn't it? Yeah. Yep, very good. You guys got it. So we use the Doppler effect, Doppler shift to know about this motion we call radial motion. This is proper motion now. I'm kind of going back and forth on you a little bit. So this was what, 20 years apart? This kind of made me smile. A kind of a fun thing, I call it the flying V in the constellation Taurus. Like Taurus the bull. Goodness, come back. Taurus the bull. I wonder if... Whatever. Okay, Taurus. This is kind of, I think this is kind of like up near his head. This is kind of like near Taurus the bull's head. But there's this star called Barnard star, and it's this guy right here. So do you see him, the star moving, moving, moving? Okay, so that's the proper motion. We just have to see it to believe it. And here in a minute, I've got a slide to try to kind of remind you how that works, but you can only see it moving like this, well, if it's moving side to side, but also it has to be relatively close. Because like, if I have that movement, but it's a star way out there, and it's just kind of moving like that, it's like, I can't detect it. So the closer the star is, we have a chance of seeing this proper motion. There, I was telling you about the Big Dipper. Yeah, we all love the Big Dipper. But you can kind of see the little green motion where the direction that the stars are going. Put another way, these stars don't care about each other at all. They're just kind of independent out there. And they make that shape because of how we are. So here we go. This is what they'll look like 50,000 years from now. Different. And this is what they look like 50,000 years ago. So, I don't know. It is what it is. Okay. So parallax, anyone? I know, do you guys remember what we did? It's just,
Yeah.
Okay, good. And we kind of went outside and did something kind of, so if I hold it out, I was kind of talking about the Barnard star. If the Barnard star is very far away, I'm not going to see it move very much, but oh my goodness, if the Barnard star is close, I see it like move a lot against the background. Oh wow. Like go cross-eyed. So I feel like this is kind of a repeat idea. The slides are kind of small. Let me see if I can kind of make them bigger here. There we go. So can you see, I'll call this one, and I can't write on it, so you'll just have to bear it. So I'll call this one A, and I'll call this one B, okay? So, and the star of interest is here. Here's the star of interest, and here's the star of interest. So A or B. And my question's gonna be, which one moves the most against the background? How many people think that A moves the most against the background stars? How many people think that B moves the most against the background stars? Very good. And remember, we talked about this before, and it's kind of like, one eye, the other eye, except this is different. This is the sun, this is the earth is here, and then the earth is here. So that's kind of like your one eye and the other eye. We're like looking at it from a different point of view. So, yep. So you guys said that this one didn't have as much movement. That would be like proper motion, okay, or movement, parallax. But this one has more movement, and this one's closer. So wonder how that goes. All right. All right. So here's the deal, though. So we can use. I should have emphasized this. Sorry. One of the things I didn't say was we can actually use this movement to get to this distance. Okay, so what is this distance? This distance is here. What distance am I describing? When I go like this for A, and I go like this for B, what distance am I describing? So here's the star, here's the sun, which basically is us. Here's the star, here's the sun. So what is that distance? What's that?
Relative distance?
Relative distance, yeah, that's all I was after. That's relative distance to the star.
You can ask us good questions.
I did, yeah. You just have to read my mind. So I was after relative distance. And actually, I'm going to spend a minute to kind of talking about how do you know how far away a star is? Because actually, that's important to know to understand the star period. So here we go. On to the next slide. Do you guys buy this, that if the star is too far away, so you guys said A was farther away, well, what if we go ahead and move that star even farther away? At some point, as the Earth orbits the sun, you're not going to see it move because it's too far away. You won't see the little wiggle there against the background stars, right? So at some point, it's too far away for us to get the distance because we don't see it move as we orbit the sun. Well, here's the deal. How far is too far away? Well, it depends on what kind of telescope you're using. First off, which telescope will give you the best images? A telescope that is down here, even if it's a beautiful one that's like 15 feet long. A telescope down here, which one will give you better pictures? This one or like the Hubble Space Telescope that's orbiting the Earth?
The space.
Yeah, the Hubble Space Telescope. So there is sort of a difference, and this says if you're using a telescope on land, okay, then it's a good telescope. You can figure on getting distances to stars that are up to about 100 parsecs. Yeah, see, I spelled that wrong. Sorry, parsecs. I put two C's, and it's one S and the other one's a C. So 100 parsecs, which is about 32 light years. If you're using a Hubble Space Telescope, instead of 100 parsecs, you get 150, which makes sense. So it's all about see a star, catalog it. See a star, I kind of go back to those gals who looked at those Severin spectral types. Okay, we're all about categorizing things. So scientists have done this for about 2.5 million stars. They have calculated distances of 2.5 million stars. Sometimes I think people that are looking through our telescopes and coordinating all this information and doing the math to figure out these things, they just have the patience of Job or whatever. Okay. Stars. This is actually a set of stars that are in a misnamed, something very misnamed, I think. It's called the Small Magellanic Cloud, or the SMC. I'm going to show you what this would look like in this nighttime sky. But the Small Magellanic Cloud is on my bucket list. It's only in the southern hemisphere that you can see this. It's a galaxy. It's a relatively close galaxy. My problem with calling it the Small Magellanic Cloud, and it's a galaxy, is what were you thinking? You know what I'm saying? Okay, anyway. cluster of stars in the Small Magellanic Cloud. It's located about 200,000 light years from us, and so heads up, like our galaxy, the Milky Way is a galaxy. The Milky Way galaxy is only about 100,000 light years side to side. So 200,000 light years, 100,000 light years, you're like, it must not be in our galaxy. All right, but you guys told me the different colors of stars. Okay, you guys told me blue, I see red, I see kind of whitish. Okay, so yeah, here is the Magellanic, the Small Magellanic Cloud that again we can't see in our hemisphere. And here is the Small Magellanic Cloud. I think that is a globular cluster, I think. But that's a galaxy, it's like an irregular galaxy. This is, if you're in the southern hemisphere, I have another picture to show you. This is the Small Magellanic, like Magellan, like a Thor, not Dora, but Magellan. It's a Small Magellanic Cloud. This is a Large Magellanic Cloud. And you can kind of get a sense of scale maybe. This is like some beautiful landscape in the southern hemisphere. And if your skies are clear, actually you can photograph these. And that might be a meteor shooting between the Small and the Large Magellanic Cloud. I did not take this picture. I see that's gorgeous. Okay, so what did we talk about so far? We've talked about stars. We talked about the different spectral types, kind of corresponding to different temperatures. We talked about we can get to the distances of stars. One of the ways using parallax. Yeah. What else about stars? Well, one important thing about stars is oftentimes they have a buddy. Like you guys have buddies, okay? So they have a buddy in part because they were born in kind of the same stuff that gave them, they're not twins, well, sort of twins. Yeah, they have twins because they were kind of born in the same womb, the same nebulous material. So most stars are actually binary stars. And I'm going to talk you through the different types of binary stars. So these are stars that are close to each other, okay? Now, there's some stars that look close to each other, but aren't really. Those aren't true binaries. Those are what we call visual binaries. And in order to be different type of binaries, it's like, how can you tell? Well, here's one way you can tell. If they are, and I'll underline the word visual, if you can literally see two of them, they are a visual binary. There's all sorts of examples of that. Sirius was the dog star. Remember in Canis Major, a star called Sirius in Canis Major, that's the hunter's dog. So we have a Sirius A and Sirius B. They're actually, you can see them. They're visual binaries. Another example of a visual binary, okay, see the Big Dipper? I'll make it bigger here. See the Big Dipper? Oh, come back. Ooh, come back. There we go. Big Dipper, right? And the handle of the Big Dipper right here where the second one in actually is a quartet. There is Mizar is the bright one and Alcor is riding on top of Mizar. And then if your telescope is really good, you can get that resolution where we call it splitting. You can take this guy and split it into these and take this guy and split it into these if your telescope's really good. All right, that's weird how that does it.
They have like 4 suns in like one little area there.
Mm-hmm. 4 stars, yep, in one little area there. Exactly. Agreed. Here's one for you. Unfortunately, you can't always see them. Okay, if they're not visual, we got to kind of do some detective work. Here's one for you. A spectroscopic binary. And I'll try to kind of show you what that would look like. Ooh, come back. They finally got the clocks fixed in here. So this is a binary star system. You're like, almost looks like a planet system. But the red and the blue are stars. Does it look like the blue star is orbiting the red star? You're right. Okay, so here's how this works. If we're over here, we talked about the Doppler effect, the Doppler shift. If this blue star is moving towards us, what sort of shift should we see in the lines from that?
Blue shift.
A blue shift. So those, let's see, I see 1, 2, 3, maybe 4 over here. Those lines should go towards the blue end. Okay, over here now, it orbits, this star orbits the other star, its companion star. Now it's moving away. What should we see those spectral
A
lines?
redshift.
Redshift. So compare this, you told me blue shift here and red shift here, and you can kind of see those lines, blue shift and red shift. So here's a deal where we cannot see the blue and the red, but we can see some sort of weird we see a blue shift, red shift, blue shift, red shift. And you're like, dude, there is something weird going on, and that's what's going on. The other one's a little bit of detective work too, the last one, and it's called eclipsing binary. What happens during a solar eclipse? Let's clear back in units. Last unit. What happens during a solar eclipse?
The sun,
Sun.
the moon. Okay, so
Moon.
the sun's here,
Sun.
Earth is here,
Earth.
and the moon somehow gets in the middle.
Yep.
The sun.
And that's exactly it. It's like a new moon phase. Yeah, exactly. So that's a solar eclipse. And so of course the light we see from the sun goes way down. Basically, yeah. So here's the deal. With these, see if I can make this big again. Here we have a blue star. Now the blue and the red here, these are stars. That's not a star and a planet. Okay, that's a red star and a blue star. Here's how this works. So we're over here, we can't tell there's two stars, but we're trying to figure it out if there are. When they're side by side, our light curve is at its max. When the blue star goes in front of the red star, it takes a little bit of the red star and it eclipses, just a little bit of it. What happened to our light?
It went down.
It went
Just
down.
a little bit.
Just a little bit. It comes over to the side, what happens to the light?
We're back to the same.
Back up. So here, the blue star scurries behind the red star from our perspective. What happened to the light curve? Went way down. So this is, again, we kind of tease the information from that pair of stars. So if you see a light curve, you're like, what? And then you get to looking at it, and this is cyclical. Okay, so it's pretty cool. So 3 ways of seeing that there's a pair of stars instead of just one. One is visual, and the other was this one using spectroscopic binary. And then this one is what we call an eclipsing binary. It's weird because you're like, well, they're just a pair of stars. Why do you use those names? It's how we found them. Well, did we find them visually? Did we find them using the spectra? Did we find them using the eclipse method? So that's it. So this one, if you watch that, there was a movie years ago about these tall blue aliens on Alpha Centauri, a planet that was orbiting the star Alpha Centauri, I believe. But in Alpha Centauri, or in Centauri, which is a constellation, there are actually 3 stars that are really close together. And that's what this slide, and I was looking at, it doesn't do a whole lot for me, but there are 3 stars very close together. Okay, and I feel like these are kind of review slides, what I just said. What kind of, is this right? 2 stars orbiting each other. Oh yeah, okay. So this is sort of what I was talking about. This is different in that you don't have a big red star in the middle and a blue star going like this. Instead, this is maybe more what happens. In the case we looked at before is because the red star was bigger and the blue star was smaller. Now we have like a pair of stars, and they do a dance around something called a common center of mass. So can you see that dance? So I would be the common center of, oh, I can't do that. This would be the common center of mass, and the stars, I'll do it this way. This would be the common center of mass, and the stars kind of go like this. That's actually what this figure is showing you. I'm trying to do it, so, okay. So the stars are going around something in the center. Now I'm going to turn it this way, and now look for the Doppler shift. So they're orbiting common center of mass. This one goes towards you, this one goes away. So what sort of shift do you have here?
Blue.
Blue. Going away?
Red.
Red. Now, what if they're going to go like this? What sort of Doppler shift do you have? Are they going towards you or away from you?
Neither.
No, nothing. And then we go over here. So now what do you have with this guy?
There's red with that one and then
Red with that one, blue with that one. So it's just taking that, tediously taking those information and trying to look for those shifts. It's exactly what you're seeing here. Eclipsing, I bet you guys will buy this one. We talked about this one before. What position, 1, 2, 3, or 4 would have, and actually there's 2 up there, would have the most light coming from that pair of stars? What do you think? What do you think, which ones would have the position? So we have the little star orbiting the big star. When here on Earth are you going to see the most light coming from those? 3 and 4? I'm thinking 3, but I'm thinking 4 is going to eclipse a little bit of the red star. So 3 is 1. What about the other one?
1.
Yep, 3 and 1, max. When are you going to have the least amount of light coming? 2. Position 2, exactly. That's the eclipsing method. You guys got it. You said 2, the least amount of light, and you said 1 and 3, the most amount, and then 4 actually is going to be somewhere in between. Very good. All right. So we talked about a lot of things, and with motion, finally, with motion, if it has a companion star, which I've read 2/3. I think that said 1/2. I've read like 2/3 of stars that we look at in the nighttime sky actually have a buddy star. Does the sun have a buddy star? No. We actually, some people have toyed with it. Used to have one, but no. And I think they even call it the nemesis. If you can catch 2 stars having a buddy and you can see them moving, then you can get to the mass of the star. Okay. Well, I think I have like 2 more slides, but I want to take my time. So bring these when you come Wednesday, and we'll knock out both of those parts and probably begin the next one. And hopefully see you on Tuesday. If you have any questions, let me know. But 10:30 to noon. So, but it takes about 20 minutes. It doesn't take an hour and a half. Oh, how about my binoculars?
Yes, they are at home still.
Can you bring them Wednesday?
Okay.
Okay, thanks. There's one. Glad you got that done.
I'm